So at the top of this, I have two definitions of what it means to be independent. We really only need one of these, okay? If two events are independent, then the probability of A happening by itself will be exactly equal to the probability of A, even if you restrict your population to B, A given B, okay? So here's a different version of this, same thing, and you're going to find there's different options as to what you want to calculate to determine independent or dependent. But what's important is the probability that stands alone, and in this case it's B, has to be the first within the given statement, okay? So let me give you an example. If I just change my variables, if I look at the probability of R given S, what should that equal if it's going to be independent? Probability of R. It's always got to be that first letter, okay? I'll give one more chance. If I have the probability of X given Y, if it's going to be independent, what does that have to equal? Probability of X, correct, yep. So as long as that first letter is the one that's all by itself as well, you can do it in any order, okay? Oddly, I'm just going to jump down to exercise 3 because it jumps right into the tables, and I think that a lot of times that's the way the information is going to be presented. So here we have, yeah?
In this science category, 6 plus 4 doesn't equal 9.
In this, oh.
But all the totals worked out with that. Is it for English?
Well, that's weird.
No, right.
Because I stole this from something.
Like if you add up all the fees.
Yeah, no. I see what he's saying.
You just throw it out.
No. So all these do add up to 30, but this should add up to 10. All right, we're going to pretend like we don't notice that, and we're going to take it for the numbers that they are, okay? But you're absolutely right. I took this from, where did I take this table from? Well, I didn't make it up, I can tell you that, but
Sure.
I'm positive. It would take me way too much time to create a table, and all right. Pretend we don't notice that, but good catch. All right, so a survey of 57 sixth graders was done to determine which subject was their favorite. The results are shown in the table, sorted by gender. So what we're looking at here is the favorite subject of a person independent or not from their gender? What do you guys think, just without doing any calculations? Do you think your gender has something to do with which subject you like the best? No? Mr. Wideman, what do you think? Oh, shoot. No, it's okay. I feel like a lot of guys, and maybe this is just gender bias, but I feel like a lot of boys like history best.
Compared to what?
Do you think gender has anything to do with favorite subject preference?
I do.
Yeah, I do too.
That doesn't mean that's where they should
Right.
focus, obviously.
Right.
I think.
And that doesn't mean there's not exceptions, but I'm sure there are some girls that love history, but I feel like history is a good example where it tends to be boys that love history. Scott's saying no, you might be an exception. And I think, of course, but generally speaking, I think that we might find that there is a relationship between gender and favorite subject. Part A, but we're going to have to do calculations to back it up. We can't just go with what we think. So I was just kind of having fun with thinking about that concept. Part A says, does it appear, based on the data, that the preference for math as a favorite subject has dependence on gender? So we're specifically looking at math. So there's a bunch of things we could calculate, and I'm going to give you options. We could look at the probability of math versus the probability of math given male. I can't use an M again, so I'm actually going to write out the gender. Or I could look at the probability of mass versus the probability of mass given female. It didn't specify that I had to do it towards males or towards females. I also can flip this around. I could do the probability of male versus the probability of male given mass, or I could do the probability of female and compare it to the probability of female given mass. There's 4 different ways I can do this. I just need to pick one of them. Okay, we all should get not necessarily the same numbers, but we all should get either they're equal or they're not equal. And if they're equal, they're independent. Okay? So let's look at the probability of being a male. All in all, what's our probability of being a male? How many males are there? How many total people? 27 out of 57. Very good. And I'm going to compare that to, and here's where our conditional comes in. Oh, I wasn't supposed to be probability of male. M is standing for mass. We got to back up. What is the probability that someone likes math? 18 out of 57. Sorry about that. Of course I make it confusing with 2 M's. Now we're going to look at our conditional probability. What is the probability of liking math given that you have to be a male? Say it again, Hunter. 10 out of 27, because we're restricting our population to males. So we're just looking at these 27. Out of those 27, how many like math? 10. And then I'm just going to calculate both those and see if they're equal. 18 out of 57 is 0.32 versus 10 out of 27 is 0.37. So, are they equal? No. So we would conclude, since I'll write they're not equal, I will say that they are not independent. And again, we all know that if you're not independent, that would suggest or usually be the same as being dependent, but they're very careful to tell us that you should not use the word dependent. They're just not independent, meaning there's maybe something, we don't know how big or how small, there's something about being a male that makes you more likely to like math. Does that make sense? Because your probability of being a male is 32%. Or I'm sorry, the probability of anyone liking math is 32%. The second you restrict your population to males, the probability that a male likes math now jumps up to 37%. So something about being a male made you slightly more likely to like math. Because both of these are probabilities of liking math. It's just this is the probability of liking math for everybody in general. This is the probability of liking math given that you're a male. Follow? Okay? Now we would be done here, but just for the sake of also, doing it again and showing you how if, let's say, Riley chose this way to do it and Jake Clancy chose this way, they should still get the same conclusion of not independent. So again, our probability of liking math, still 18 out of 57. We're going to compare that to our probability of liking math, given that we have to be a female. And Kaylee, what's that probability going to be? 8 out of 30. You have to be a female, so we're only looking at these 30 people. Of those 30, 8 like math, so 8 out of 30. So, on its own, the probability of liking math is 32%. But if I talk to the females and I ask them about do they like math, that probability is only 27%. And still, they do not equal each other, so we would say they are not independent. And we can kind of read into that and say, okay, there's something about being a female that's making people less likely to like math. Okay? And I think that's true in the working world. Math-oriented jobs, engineering is very male-dominated. Okay? Teaching is a little bit different for whatever reason. I think because teaching in general is dominated by females. Yeah. Do you feel like a minority?
Building, but
No.
if I go to an elementary
Right,
building, yeah.
right. So the fact that now we're talking about a teacher in math, it kind of evens it out a bit. So most of our math teachers here are female, but in general, math-oriented professions are dominated by males. It's just kind of a fact. So yes, we would say, you know, without using the word dependent, we would say yes, the data suggests that there's something about gender that may push you in a certain direction, okay, as far as what your favorite subject might be. Does this all make sense? Okay. Part B, does it appear based on the data that the preference for social studies as a favorite subject has dependence on a student's gender? Okay. Chance, tell me what you want to calculate. What two calculations do you want to make here and compare to help get an answer?
The probability of social studies.
Okay, and what are we going to compare that to?
Probability of taking social studies, liking social studies as a male.
Given a male. Perfect. Okay. Margaret, what do you think? What's the probability of liking social studies? Perfect, 19 out of 57. And we're going to compare that. What's the probability of liking social studies given that you are a male, Morgan? Out of the males, 27, 9 like social studies. Perfect. And we're going to compare those. 19 out of 57, 33% of people like social studies. Versus 9 out of 27. Also 33% of, even if you restrict that population of males like social studies. So those are the same. So these are independent of each other. Because restricting your population of males didn't have any effect on the probability of liking social studies. The probability of liking social studies was the same in both cases, whether you restricted your population of males or not. Follow? Good. All right, flip over. We're going to do the same thing, but it looks like, with this paragraph they've presented us with, it looks like we're going to have to create our own Venn diagram. We've got a probability that a person is left-handed, the probability that they have brown eyes, and the probability that they have brown eyes and are left-handed. So what should the two titles for my circles be in my Venn diagram, Jake Phillips?
Brown eyes, left-handed.
Perfect. Brown eyes, left-handed. Did they give us both? The overlap they did? What is that? 2%. The probability they have brown eyes and are left-handed, 2%. Perfect. So they also told us the probability of being left-handed was 12%. So what should go in here, Alexis? Here's the sentence we should be looking at. What goes in here? 10, exactly. Because the total in the circle needs to be 12. And now 10 and 2 makes 12. And what should go in here, Anthony? 40. Because the brown total should be 42. And then what should go out here? Jake Bender?
I don't know.
I need you to pay attention. You can, what are all these all 4 percentages supposed to add up to? 100, so what's missing? 48. Okay? Alright, now, I haven't even looked at the question. Is the event of having brown eyes independent of being left-handed? Support your answer. So, Kaylee, what 2 probabilities can I compute and compare to get at this answer?
The probability of having brown eyes, and then versus the probability of having brown eyes, given your left-handed.
Perfect. So what is the probability of having brown eyes? 42%, right? Look at your brown circle, 42 out of the total of 100. So we'll just say 42 out of 100 versus the probability of having brown eyes given that you're left-handed. What is that fraction going to look like, Cole? Probability of having brown eyes given that you're left-handed. So what should we start looking at first? Left-handed people. What's the percentage of left-handed people? 12. So out of that 12, how many of them have brown eyes? Out of this 12. Once you restrict your population to given that you have to be left-handed, you can no longer look outside of this left-handed circle because you're only asking the left-handed people. And 2 out of the 12 have brown eyes. So 42 out of 100 is 0.42, and 2 out of 12 is 0.16. That's a big difference, right? So since they are not equal, what do we say? Not independent. Which suggests, although we can't say it conclusively, we suggest that something about being left-handed is making these people less likely to have brown eyes. See how their probability went down when you restricted it? The probability of having brown eyes went down significantly when you were talking to left-handed people. Is anyone in here left-handed? Blondes? You like that? That's funny. Wonder if there's a thing there. You'd have to do more studies, but you get the point? Good stuff? Any questions? Okay. We're crossing this out. I forgot I decided to cross that out. Jump to 6. Suppose you have 7 CDs. 4 are rock, 1 is jazz, 2 are country. Today you choose 1 CD without looking, play it and put it back in the box. Tomorrow you do the same thing. What is the probability that you choose a country CD both days? So we are a little bit away from the conditional probability and the independence thing. But let's kind of list out our sample space. We have rock, 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 jazz, country, country. Today you choose 1 CD without looking, play it, and put it back in the box. Tomorrow you do the same thing. What is the probability that you choose a country CD both days? This is the probability of choosing a country and, on the second poll, also choosing a country CD. What do you know about and in probability? I'm seeing a few of you mouth it. Say it. Multiply. Exactly. So on your first draw, you're looking for your probability of choosing a country times, on your second draw, your probability of choosing a country. Austin, what's the probability of choosing a country CD? 2/7 times. And and remember, you put that CD back. So on the second day, there's still 7 CDs, and still 2 of them are, 2 out of the 7 are country, again. So when we multiply, we get 4 out of 49. As a decimal, that's 0.08. 8% chance. Okay, and on the last one, 50% chance of thunderstorms Monday, 50% Tuesday, 50% on Wednesday. They say assume these are independent events. I'll tell you in a minute why they're telling us this. What is the probability that there will be thunderstorms on Monday, Tuesday, and Wednesday, all 3 days? So the probability of thunderstorms Monday and Tuesday and Wednesday. So we have to look at each one separately. So 3 separate events, 3 separate probabilities. The probability on Monday was 0.5. The probability on Tuesday was 0.5. The probability on Wednesday was 0.5. So the probability that we're unlucky enough to have these on all 3 days, Monday and Tuesday and Wednesday, this multiplies to 0.125, which is approximately a 13% chance. Okay? Here's the thing with that multiplication rule. And only turns into multiplication if the events are independent. So that multiplication rule can only be used if the events are independent of each other, which, whether or not we have thunderstorms on Tuesday doesn't have anything to do with whether or not we have them on Monday and so on, so those are independent events. Okay, same thing, whether or not we chose a country CD on Monday has no bearing on whether or not we pull a country CD on Tuesday. If you want your review sheet now, you may grab it from me. There you go. If you're not going to be here on Friday, you need to take the test tomorrow after school. Questions, you can ask me tomorrow. Perfect. Thank you. I'm still recording.